Hey, welcome to another episode in my mini-series on protocols and software development. Last time I showed you two fundamentally different ways you can use them in Swift, as existential types and as generic constraints. Today I invite you to delve deeper into the topic of protocols performance. We'll see what happens when you call properties and methods declared in a protocol and how you can make them work faster. If you learned something new from this video, I'll appreciate you giving it a thumbs up or leaving a comment. And if you're interested in more content on software engineering, subscribe to the Codebird. I just had a video about method dispatch in Swift, and this topic is going to be essential for what we're discussing today. I don't want to repeat myself, so if you haven't seen that video, I really recommend you to do so right now or after watching this one. In short, the term method dispatch refers to how the programming language links calls to functions with their actual implementations. To execute some instructions, the runtime needs to dispatch that call to the implementation. Swift supports multiple modes of method dispatch, and static or direct dispatch is the fastest of them. From the previous episode on protocols, you may remember something about the existential container. Basically, when you use a protocol as an existential type, Swift creates this wrapper box that intercepts and proxies calls to the implementation object. But what is this container really, and how does it work? The existential container is a concrete data structure. Its job is to receive calls for protocol properties and methods and forward those calls to the correct implementation addresses in memory. The structure of this container fully explains why using protocols as existential types has negative consequences for runtime performance. The existential container has three key parts. First is the conforming value, or perhaps more often just a pointer to the object on the heap. Second is the value witness table. It's not very important right now, because it's basically just a set of functions that help manage the value, create, move, or destroy it. But third is the most crucial part. It's called the protocol witness table, and it contains the addresses of the properties and methods that satisfy protocol requirements. Here's how it all works together. When you use a protocol as an existential type, Swift will derive an existential container from it. When you then use a property or method, your call will be directed to this container. And to actually execute the requested behavior, the runtime needs to do three things. First, it looks up the address of the implementing symbol in the protocol witness table. Then it gets the value, which is the implementation object. And finally, it dispatches the actual call to the memory address while using the value as the hidden self-parameter. From this mechanism, one that has a separate structure for looking up methods at runtime, it is quite clear that using protocols as existential types involves dynamic dispatch. Just like classes vtables, protocol witness tables enable polymorphism, but at the cost of proxying every method call just as it happens. This indirection is the key reason why existential types have a performance impact at runtime. And for situations where you can't afford to pay that price, Swift offers an alternative way, using protocols as generic constraints. Let's see how they differ. In the previous episode on protocols, I mentioned that when you use a protocol as a generic constraint, the compiler mostly uses it for type checking at compile time. In the best case scenario, it will then erase the protocol entirely, leaving only the calls to concrete objects that implement that protocol. This process is called monomorphization, or specialization. It's when the compiler sees polymorphic code and transforms it to separate specialized versions for each concrete type. Monomorphization results in more instructions embedded in the executable, but it's not a big deal compared to the two huge benefits it provides. First, everything happens behind the scenes. You never see this generated code and you don't have to maintain it. And second, everything happens at compile time. The system doesn't need to proxy and resolve any function calls at runtime, which is a huge performance booster. By baking the concrete types into the resulting IR and then machine code, the compiler can enable static dispatch, where method calls link directly to their implementations. This is the best outcome, but it is far from guaranteed. You see, Swift uses a hybrid approach for generics. It will decide whether to monomorphize them based on a few signals that it collects at compile time. For example, using implementations that have static dispatch, enabling whole module optimization, or making the function inlineable increase the chances of it getting replaced with a specialized version. But in many cases, you may just get polymorphic generics. They work through something called the generic box. This is the default mechanism for generics, and Swift falls back on it when it can guarantee a high degree of optimization. That is often the case when you use generics across module boundaries or when you optimize your codebase for its size. With polymorphic generics, the compiler will still emit generic functions, which means they'll be using dynamic dispatch at runtime. But there are two important distinctions from using protocols as existential types. First, even when generics aren't completely specialized, the protocol itself is still only used for type checking. When the code is compiled, the protocol's requirements become the methods of the generic type itself. In other words, the protocol effectively doesn't exist at runtime. And second, even though you haven't achieved real static dispatch, the generic box works faster than the full existential container. That's because the latter has a fixed size for the implementing object, and that size often requires the object to be stored on the heap and retrieved separately for each function call. In contrast, the generic box can store the value itself and pass it to the function directly. I know it's a lot, but we're not done yet. So far, I've only talked about the core protocol requirements, the properties and methods you declare in the protocol itself. These symbols are known as points of customization. But in addition to them, you know that you can also declare symbols in protocol extensions. And they are entirely different. Because these symbols are not part of the protocol declaration, they are not considered points of customization and they don't enable polymorphism. You can't implement those symbols in the conforming object. Instead, you must do so right in the protocol extension. And because there's no polymorphism, Swift can heavily optimize the execution of those instructions. That is why protocol extensions always use static dispatch. This is really good for runtime performance. But it also results in one tricky situation that can make the behavior of your code less intuitive. Let's have a look at this and a few other interesting scenarios. The tricky situation is this. You've got a protocol with one required method. This method has a default implementation in the protocol extension. The extension also declares another method that's not part of the protocol. Then, in the conforming object, you implement the protocol's required method, even though it's got a default implementation. But this object also declares a method whose signature matches the non-required method in the protocol extension. Finally, you instantiate the object and use it three different ways: as a concrete, existential, and generic type. The question is, what will be the result of calling each method? When you use the implementation directly, the compiler and runtime know nothing about the protocol. For that reason, they always use the methods declared on the object itself. For an existential type, the result is slightly less intuitive, though still fully expected. The runtime doesn't know much about the concrete type, besides that it exists and implements the protocol. When it encounters a call to the protocol requirement, which is a point of customization, it is designed to consult with the protocol witness table in the existential container. And the rule is that the concrete implementation always overrides the default one. Because of that, the runtime calls the methods from the actual class, not the protocol extension. But when it sees the method that's not a point of customization, it calls the version specified in the protocol extension. That's because the runtime has no knowledge of the concrete type. And here's the most surprising scenario. When you use the protocol as a generic constraint, the compiler does know about the concrete implementation, but the runtime doesn't. Since I'm using a struct, which guarantees static dispatch for the implementation and improves the chances of generic monomorphization, you might expect to have the implementation's methods called in both cases. But that's not what happens. Just like in the previous scenario, you get the required method from the struct, but the non-required method from the protocol. Confusing, right? This behavior can be explained though, at least to some degree. You can view the transformation as a two-stage process. First, even if the compiler fully specializes the generic placeholder, the generic type still receives its methods from the protocol. At that stage, the struct's non-required method is just ignored. The generic type now has two methods, and one of them is configured to use the protocol witness table and resolve the required method at runtime. But then, at the second stage, the compiler decides that the protocol requirement can be optimized even further. This time, it replaces the protocol witness table with a direct call to the implemented method, therefore achieving static dispatch. That's what happens here. While we can't guarantee the result of the second stage, we can say for sure that the non-required method from the conforming object will be ignored. Protocol extensions always use static dispatch, and because of that, the compiler doesn't even try to look for any alternative implementations. As you can see, the underlying mechanism of protocols in Swift is quite complex and isn't always fully predictable. But what we can do to achieve better performance involves providing the compiler enough signals to optimize as much as possible. The good news is that many of these principles aren't limited to protocols. They can be applied in most other situations. For example, using value types such as structs enables static dispatch by default. Also, generics, even if not fully specialized, they still work faster than type erasure through existential containers. But the key idea that I'm trying to convey in every video on this channel is that all these things are just means to an end, or tools. Yes, ideally you should master these tools, though not because they're valuable in themselves, but because they help you design the overall system in the most robust, efficient, and extensible way. And that is what gets you to the end. This has been the final episode in my mini-series on protocols. I hope these episodes have given you enough to use protocols with confidence and proficiency. But if you have any questions, leave them in the comments so I can do a follow-up video later. If you found this episode helpful, give it a thumbs up. Subscribe to the Codebird for more engineering content coming soon. Stay tuned for the next video, and until then, make your protocols fly.